Hello everyone and welcome to this next lecture on Python Power Electronics, and this is a continuation of the previous lecture in operation and control of an uninterruptible power supply UPS. So going over to the file section, in the previous lecture I had already extracted this single UPS simulation collection, which is basically the collection of simulation files, and within this I had covered the basic concept of a PWM switching, but not the PWM switching but a square wave switching. So basically what I had shown was how a square wave switching can be used to achieve a square wave, or rather rectangular. A rectangular wave would result in a fundamental sinusoidal component such as this one, but unfortunately along with the sinusoidal component there will also be several low frequency harmonics, and this is the biggest problem, these low frequency harmonics. So in this pulse width modulation, in this next lecture, I'll be talking about the next concept, which is called pulse width modulation, and I'll be talking about how pulse width modulation produces certain improvements in terms of harmonic components. So as before, we will start off with the same mold circuit. The circuit will be exactly the same. And this is the circuit as before. It is one leg of an inverter, so basically two switches, an upper switch and a lower switch with the midpoint, and there are two DC voltage sources. There's an upper DC voltage source and lower DC voltage source, again with a midpoint, and we are measuring the voltage across this midpoint. So in the square wave modulation, we were keeping the upper switch on for the entire half cycle when the sinusoidal voltage was positive, and we were keeping the lower switch on for the entire half cycle when the sinusoidal reference waveform was negative. So basically there was a rectangular waveform, which is what I showed you last time. Now in this case I'm going to show you another way to simulate the circuit. So let's go ahead and start off my simulator. So first and foremost I shall see into the virtual environment. I need to activate the virtual environment. So now I'm in it. Now that I'm in it, and now I can launch the circuit simulator. So it is python manage.py run server. So it all starts up, no issues. So let me go over to my web browser and let me access the web link. So this is the web link. There are two simulations. Previous one was single phase square wave modulation. In this case I'm going to start a new one. Now this is the simulation. Let me also go over and check out the control files. So in PWM concept there is pulse width modulation. So here there are two control files. There is pwm.py and there is Fourier analysis.py. So let's look at pwm.py. So in pwm.py, again there is the same old reference sinusoidal waveform, that hasn't changed. The only difference is there is now a triangular waveform. So this is the generation of the triangular waveform, and I'll show you this by plotting the waveform. And before I was comparing the reference waveform with 0, and when the reference waveform is greater than 0 I'm turning on the upper switch, and when the reference waveform is less than 0 I'm turning on the lower switch. Now I am now comparing not with 0, but I am comparing with a triangular waveform. Now it might seem a little strange, but through simulations I'm going to show you how this works. And the Fourier analysis is the same old file. It is just basically measuring the output voltage and calculating 15 components of harmonics based on this, that is DC and up to 14th harmonic. And we have calculated several of these components, that is the fundamentals, the third harmonic, the fifth harmonic and the seventh harmonic, and besides this I'm also calculating the sum of all these harmonics. So these are what we are going to plot. So let's get started. Let's go and start off with a new simulation. So we shall call this single UPS, and let's call this PW. Okay, let me copy paste it here. I don't want to write more. You're always welcome to have a very large description, but anyway I'm not going to do that. And let me know, go to the properties and copy the path. So this is the path of the file of the folder. So this is that path. I shall save this. If it saves, no problem, it has been able to get that path. So now there is only one file as before, that is inverterleg.csv. So let's add that. And let me call this inverterleg. So there is only one file, so let's just click on process circuit schematics. So we have processed the circuit schematics. There are no errors. The circuits do not have any detectable errors, so we can continue. Let's go back to the main page and let's now edit the circuit parameters. So first let's view the components. And these are the components. Now as I said before, you can actually go and manually edit each and every component parameter. So you can click on edit parameters, you can change the parameters, you can save the parameters, and it will be updated. That's one way. In this case, if you get the simulation package, then you will be given this file, that is inverterleg params.csv, just as in the previous case, which is a parameter file. And if you have a parameter file such as this one that has all the parameters of all the components in this circuit schematic, you can merely upload this file, and that's what I'm going to do because I'm going to save time here. So let me just upload this. Click on the upload button. And all the parameters have changed. So with this I can go back to the main page, and now I can edit the control. So as I said before, there are two files, so let's add both of them. One is pwm.py and the other is Fourier analysis.py. So now that we've added the two control files, let's configure them. As before, all we have to do is upload the descriptor. If you have downloaded the simulation package, you will have this descriptor. So let's open this, upload it. So initially it's all empty, and now that it has been uploaded, you will see the database is complete. So let's go back and let's configure pwm.py. So again, I will upload the descriptor file. And these are all the variables of the descriptor file. So now that we've done all this, we are now ready to run the simulation. So let's go to view output. So first and foremost, I will click on run. Okay, it says running, but as I said, always go over to the terminal and check if there is any cryptic error message. Right, there are lots of error messages which may not be reflected in the web page. There is none. So we are good to go. So this simulation is going to take some time to run. So what I'm going to do is I'm going to pause this video and I'm going to come back. So now that the simulation has been running for a while, let me now start adding some plots. So first and foremost, simplest thing, let's just check the output voltage. So let me click on start plot and let me plot the output voltage. So I should call this save waveform, and let's just plot this to begin with. So I click on the plot button and let's go over and check what it has plotted. Now the first thing you see, it's a stark difference. Before you were seeing a rectangular waveform, now you see it's just one solid blue color. What this means is it's actually a highly switched waveform. Alright, so now let's go and zoom in on some particular point. Let's go zoom in between 0.07 and 0.08. Let's do that. So you can always use this zoom function. So if you add any range between these two, it will zoom. Only thing you must remember, this range has to be valid. So if you add an invalid range, it will plot the entire thing again. So let's click on the plot button. and you see this is what you get. Maybe we should plot 0.06 to 0.08 because then you'll get an entire cycle. So it has plotted again, and this is the output waveform. So you see the difference? There's a huge difference. This waveform seems like a high frequency switched waveform, and it is a high frequency switched waveform. But actually within this waveform there is a hidden pattern. I'm not sure if it's very obvious, but you see here there is actually a sine wave embedded within this. There is a sine wave. So if you see here, if you track, it goes this way. Alright, now to know what this is, we need to know what the PWM is doing. So let's do that. For some reason this is hung. Yeah, okay. So let's go back to our file and check what the PWM does. So now you see there are three things here. There is the switching function, there is a modulation signal which is the reference sinusoidal signal, and there is the carrier frequency. So what is this carrier frequency? Alright, because it is this carrier frequency which is compared with the modulation signal to produce the switching logic. So let's plot these three. So to continue with it, let's click on the add plot and let's call this PWM switching. So we need three signals. We need the modulation signal, which we shall call M. We need the carrier frequency, which we shall call C. And we need the switching logic, which we shall call SW. We will save this waveform and we can click done because we are done. So let us plot it in the same range as we did before. So that's 0.06 to 0.08. Okay, it is plotted. Let's go over and check through. Okay, so now do you see what's happening? This is okay, it's still not at all clear. So what I'm going to do, I'm going to zoom in between 0.065 and 0.07, because now we are actually looking at three waveforms instead of just two, instead of just one, and that's the reason why it's tough to see. Alright, so this is the process of PWM switching. Now you see here the blue line is modulation signal, which is the reference waveform. The orange line is the carrier frequency. It's actually a triangular waveform. Alright, it's a triangular waveform, and this comparison between these two results in the switching logic, that is the green one, SW. Alright, now I still think we haven't chosen the right one, so let me go zoom in between 0.067 and 0.7. Okay, this just shows you how finite it is, how fine or rather minute this is. So, and quite often while debugging your control and while debugging many circuits, you will need to fine tune your zoom parameters. Okay, so now this is slightly more clearer. So you see here, this triangular waveform is being compared with this blue waveform. and when the crossover takes place, you see a switching happens. Now the way it works is this: when the modulation signal is greater than the carrier frequency, that is, when the blue line is greater than the orange line, the switching is high. You see here, this is when it happens. This particular frequency, let me zoom in here also. At this particular, let's say, or rather here, let's say, at this particular point, or rather at this particular point, the blue line becomes greater than the orange line, and that's when the green signal goes high. And at this point, the blue line becomes lower than the orange line, and that's when the switch becomes low. Right? So when the modulation signal is high, you see here the width of this signal, switching signal, is at the highest. And similarly, let me go and plot. Okay, it's stuck. Okay, this is one of the problems of actually dealing with graphics. Sometimes it just gets stuck. So let me go to 0.06, or rather 0.06 to 0.065. So this shows the other extreme. You see here, this is when the reference waveform is in the lower half. Alright, it's actually crossing, but you'll see here it's at the lower half, here it's going towards the high half. And here you see the pulse width is actually changing. At this point, when the modulation signal, or rather reference modulation signal, is at its almost negative maximum, that's when the pulse width is at its almost minimum. And here you see the pulse width is almost at its maximum. This shows the concept of pulse width modulation. Alright, before it was just one positive signal, one negative signal, but now the pulse width is what changes, and it is this pulse width that is producing the sinusoidal waveform. You see here, the pulse width is following the sine wave. Alright, if the pulse width is following the sine wave. Now what does this mean in terms of Fourier analysis and frequency components? And that's what we are going to investigate next. So as before, just with this, we shall create another plot, right? And we shall call that Fourier components. Yeah, we have it saved from the previous one. And we will add Fourier fundamental. So we shall call this V1, save it. We shall add Fourier component 3. Call this V3, save it. Add Fourier fundamental V5, call this V5. And we should call this V7. Alright, so now the idea is to compare this waveform with what we got with the square wave modulation. So let's plot this. Okay, it's done. So let me go over and plot it. And you immediately see the difference. Alright, let me go and let me pick out the other one. And let's put these two together. Put these two together. So this is square wave and this is PWM, and the difference is almost immediately obvious. Alright, here you have a third harmonic which is almost 50 volts. Here the third harmonic, fifth harmonic, seventh harmonic are almost negligible. Look at this. This is 25. Alright, and the scales are almost the same. But these lower frequency harmonics, which are so very significant in square wave modulation are now almost negligible. Why? Because we are not following a square wave, we are not using a rectangular waveform anymore. We are having a pulse width. The pulse width is changing with the sinusoidal frequency, with the sinusoidal modulation signal. And that's the reason why this is way better in terms of Fourier components. Alright? And just for the sake of it, I guess my computer is a bit old. We shall also add another plot where we'll plot the output voltage, and we have this from before. Compare fundamental. We will plot the output voltage V out. Save this waveform with the fundamental Fourier funda. And let's click done. Let's go to this is PWM. Let me go and pulse width. And in pulse width, this is our compare fundamental. Apparently is having a bit of a tough time dealing with the graphics in these images. That's all I can guess. Let me open square wave just for comparison. I still don't have it. Okay, now it's opening. So you see here, this is VO, the blue line is the actual output voltage. That actual output voltage is a switched waveform, which is why you see it as a solid blue line, right? You're seeing it as a solid blue rectangle. It's not actually a solid blue rectangle, it's a switched waveform. And the orange line is the fundamental component. And you see here the fundamental component is almost matching the peaks, because there are also some negligible smaller lower frequency and high frequency harmonics which will also be adding up. But the most important thing is, in this particular thing, the lack of lower frequency harmonics. It's quite hard to believe my computer is so slow, but anyway, this shows how the lower frequency harmonics are. And as before, let's do also a plot of the sum. Now here I'm going to plot the let's call this sum of Fourier components. Start the plot, and let's only plot the Fourier sum, because there's no point plotting the output voltage because it is or we could also plot the output voltage, so let's do that. So we'll just plot this output voltage just to be consistent with what we did before, and we can say done. So let's plot this waveform. So now, apparently this is the choice that I've made, is the choice of colors. Let me just go delete that plot. It's actually quite strange the way Matplotlib actually uses the uses the colors of waveforms and therefore ends up superimposing each other. So let's call V out VO, because the first waveform is blue and the second waveform was orange, and apparently orange completely swamps out the blue. And let's plot for sum, so we'll call this V sum. And let's come over and plot this. So the sum of components, and now you see this is how it is. Now again, let's compare it. Yeah, let's compare it with this. So on the left is how the Fourier analysis, or rather the Fourier components, add up in the square wave example. You see, in the square wave example, the blue line is the output voltage and the orange line is the sum of the Fourier series components of up to harmonic number 15. You see, and these are kind of matching into each other. Alright, but here you see it's a totally different story. It's no longer a sinusoidal waveform. That's because there are some third harmonic, fifth harmonic, seventh harmonic. There is some. It's, even though it's negligible, there is some. So therefore you see the sum now is no longer a sinusoidal voltage, but this sum is nowhere close to the blue line, because the blue line is a high frequency switched voltage. The orange line is not going anywhere close to that. The reason we have only chosen 15 harmonics. So let's just do the mathematics. 15 into 60 will be 900 Hertz. We are going only up to 900. Whereas the switching frequency we have chosen is 5000. If you want this frequency to appear, you will have to actually go even beyond 5000. You may have to go up to 10,000 or so in order to achieve that kind of resolution. So this shows you the effectiveness of pulse width modulation over simple square wave modulation or rectangular wave modulation. The quality of waveform is much superior. The lower frequency harmonics are almost negligible, and the end resultant waveform is actually much closer to a sinusoidal waveform than it is in the case of a rectangular wave modulation. This may seem like an AC voltage, alright, and this may not seem like an AC voltage, the blue line in this case, but the blue line is surprisingly closer to an AC voltage, or rather sinusoidal AC voltage, than this rectangular waveform. And that's what this simulation example shows you. So as before, with this I'm going to wind up this simulation, this particular case. In the next example, I'm going to talk about the next thing. Now, as before, we cannot apply a square wave if a sinusoidal waves example is required. Similarly, we cannot apply a switched waveform like this blue waveform when a sinusoidal waveform is required. So now the question is, how do we achieve a sinusoidal waveform? And the answer to that is we have to use a filter. And that's what I'm going to talk about in my next lecture. I'm going to talk about how we can use a filter to remove the low frequency harmonics and get a sinusoidal waveform. So with this, I'll end this lecture series. I'll end this particular lecture, not the lecture series, just this lecture. If you have any doubts or comments, please feel free to message me or email me. And if you don't, just wait for the next lecture. So that's all for now. Thank you so much for listening, and see you soon.